This is on. OK, great. Yeah, so I'll be talking about atoms interlinked by light. It's a talk about some experiments we're doing, kind of expanding the toolbox for quantum simulation by demonstrating really kind of control of photon-mediated non-local interactions, in our case, between clouds of laser-cooled atoms. And this fits into kind of the broader context of what I'm sure you've heard about already this week, namely kind of cold atoms are already kind of very powerful tools for quantum simulation and more broadly quantum science, thanks to kind of the high degree of single particle control, scalability, and also control over interactions and entanglement. And that ranges from using kind of contact interactions in lattices to study Hubbard models, to using interactions between Rydberg atoms to realize high fidelity entangling gates. It's even extended to interactions between, for example, molecules in recent experiments. So this is kind of a very versatile toolbox for quantum simulation. One possible limitation of the toolbox, and the one that I'll kind of be trying to address today, is that in general, atoms interact with atoms that are close to each other. The interactions are typically local. And it turns out that going beyond that limitation can open some new directions. So just to give one, what I find kind of a motivating example, here's kind of an inspiring theory proposal from a number of years ago, pointing out that one direction that is kind of very promising in quantum simulation and quantum computation is to realize topologically ordered states that let you encode information non-locally in a way that's robust to local perturbations. The sort of, so that's great with one caveat that once you've done that, it's actually intentionally sort of hard to manipulate the information using our standard local tools. Wouldn't it be great if we had a way of, when we want to access some information that's stored in non-local degrees of freedom, controllably having a way to do that? And so that may be, for example, having some ancilla atom that via some delocalized mode of light can talk to some selected group of qubits in an array and non-destructively read out or manipulate a non-local degree of freedom in that system. So that's a nice idea that kind of illustrates things one could do if you have kind of some programmable non-local connectivity in your quantum system. And that's, just one example. More broadly, sort of expanding towards non-local connectivity opens opportunities in a number of directions in quantum science, ranging from giving efficient ways of engineering collective entangled states that have applications in quantum sensing, to, if you'd like to have kind of a hardware efficient encoding of something like an optimization problem mapped to a spin model, there you benefit from having kind of arbitrary non-local connectivity. Certain error correction schemes benefit from non-local connectivity. And also in the realm of simulation, having models with non-local interactions opens the door to studying phenomena ranging from spin glasses that we heard about yesterday to even kind of toy models of quantum gravity. So these are all kind of directions that can benefit from kind of expanding towards non-local connectivity in our cold atom quantum simulators. And there's actually a couple of different approaches to getting that non-local connectivity. And one that I think you already probably heard about perhaps yesterday from Dolev is having local entangling gates, but moving atoms around to sort of make particular effectively non-local connections. That can be very powerful, as you heard in some examples. There's a sort of a complementary approach, which is having this notion of some delocalized cavity mode. This is also used in ions, where it's some collective motional mode that gives kind of an all-to-all coupling, which can sort of very efficiently, for example, generate entanglement among many atoms or qubits. So that is sort of a very, very efficient way of generating some sort of all-to-all connectivity. And a missing ingredient there, however, is sort of having programmability of the graph of interactions. And going sort of from this top-down, let's let every atom talk to each other, and sort of add in programmability is kind of the approach that I'll be talking about today. And I think both of these are kind of valuable and complementary approaches. So I'm going to start by kind of introducing the experimental platform with some recent work on kind of programming the structure of entanglement, and in particular engineering entangled graph states in sort of a system of a few atomic ensembles in an optical cavity. And I'll use that to sort of introduce a framework for thinking about more broadly programming and more broadly and more scalably kind of really programming the graph of interactions and exploring some directions in quantum simulation from kind of toy models of quantum gravity to actually starting to tackle this problem I mentioned at the outset of can one kind of access non-local degrees of freedom in topological states. I'll give an example of using the cavity to form an interferometer for probing topological edge states. And then I will sort of mention the caveat that everything we've done in the lab, we can so far actually still easily calculate. And so sort of what's maybe the path to getting to a regime where there's really quantum advantage in this type of system. So that's kind of the outline for the talk today. And I should mention that these experiments I'll present fit into a sort of, very vibrant field of studying many-body physics with atoms coupled to light, where broadly, sort of much of the work going on, particularly with atomic ensembles, is in sort of one of two categories, either sort of engineering collective entangled states, which I mentioned. There's a sort of natural way of generating, for example, squeezing of quantum fluctuations that can be a resource for metrology. That so far has largely operated in kind of a single mode setting, and we'll be pushing to kind of more control over more spatial modes. And then on the flip side, there's a vibrant field of quantum simulations, which in some cases incorporate local interactions, for example, in optical lattices, but combine that also with the sort of long-range cavity-mediated interaction. And for all of these, the sort of basic building block for sort of how to think about this system and the role that an optical cavity can play in engineering these long-range non-local interactions, I like to start by thinking about a picture of two atoms. And asking, if I'd like these to interact by, let's say, some kind of a spin exchange interaction, I'd like to swap an excitation from one atom to the other. One way I can do that, if I have them both coupled to the same mode of light, is I can engineer some process where this atom flips a spin, that excitation gets converted to a photon that's absorbed by another atom. And in general, if I scale that up to many atoms, and they are all coupled equally to this mode of light, that will generate this sort of all-to-all connected graph. And the new tools that we'll be adding is sort of having some local optical control to program the spatial structure of entanglement and more broadly of interactions in the system. So this is kind of what the platform looks like. There's an array about 1 millimeter long of clouds of atoms. I'll show experiments where we work with anywhere from 4 to about 20 of these atom clouds. We operate in a regime where actually single atoms are strongly coupled to photons, but sort of barely in the regime of strong coupling compared to the decay rates. And so having clouds of many atoms in this case gives us really a collective enhancement in the interaction strength and the coherence of the interactions. So we work with typically 1,000 atoms per site in this system. And when we want to turn on the types of interactions I showed before, we can do that in a controllable way by sending in a drive laser that drives a process of absorbing a photon from the drive, emitting into the cavity, and flipping a spin. That process is off-resonant, the process that flips a single spin, but pairs of atoms can exchange their spins resonantly, and that gives rise to interactions between all of the atoms. And then the second ingredient we have is we can send in some light from the side, and that gives us spatial control to kind of really structure these interactions. Okay, so here's kind of an additional wrinkle that I should mention. It turns out our atoms are not spin half, but spin 1. This is the ground state of rubidium. In some of the work I'll show, we actually start with all atoms in the 0 state of this spin 1 system, and then the way you can visualize what would happen with 2 atoms is I send in light, and it can kind of bounce off these 2 atoms and turn 2 0 atoms into a pair of atoms in the +1 and the -1 state. And in general, that looks like something that could give rise to entanglement, right? I don't know whether the left or the right atom is going to be in the +1 state. And indeed, actually, sort of variants of this using local collisional interactions have been kind of long studied actually in Bose-Einstein condensates, and this is a way of generating collective entangled states in which quantum fluctuations are squeezed. And actually, sort of the first thing I'll show you is by sort of looking at the quantum fluctuations in our system, we can verify that, yes, we're actually generating entangled states, and then we're going to look at how we can program the structure of that. So in our system, this can happen at sort of millimeter scale, length scales. So here's an example of an experiment where physically the atoms are arranged in 4 clouds. So far, you can still nevertheless think of them, because they couple all equally to the light field, as being represented by some collective spin that I call F, that represents sort of the total spin of all atoms in this cavity. And because the atoms are spin 1, it turns out a full description needs to think not about sort of just the vector nature of each atom, but also about each atom's quadrupole moment. And so there's some funny variables here called F and Q, representing spin and quadrupole moments of these atoms. But roughly speaking, the picture that you can have in mind is that there's some sort of kind of SU2 subspace for describing the dynamics of this system, in which when we start with all atoms in that 0 state, we start polarized on a Bloch sphere. There's many atoms, and so there's some quantum fluctuations that scale as 1/√n in the direction, but we're roughly polarized along this sphere. And there's a term in the Hamiltonian, the spin exchange term, looks like total fx squared plus total fy squared. What this does actually in this picture is this fx squared term generates a precession about the x-axis at a rate proportional to x, and that kind of shears out these quantum fluctuations and gives rise to a state that is squeezed. And one can actually verify that by sort of looking at the angular sensitivity of this state. This is sort of the noise as a function of the angle in which I measure. One can see that the noise dips below the so-called standard quantum limit, which is the smallest it could be without entanglement. So this is just starting to verify that, yes, these photon-mediated interactions are generating entanglement in our system. So far, there's no spatial structure to the entanglement. The light talks equally to every atom. And we'd like to sort of go beyond that and start to actually have some spatial control over these non-local interactions. And so to illustrate that, I'll show you a very kind of general principle for making graph states of these atomic ensembles. So what do I mean by a graph state? Probably most people in this audience are more used to thinking about single qubits than about these funny clouds of atoms. So just to sort of first provide that context, if I had a single qubit in each site of my array, then one way I like to think about a graph state is it's something I could make by initializing each qubit in a superposition of the up and the down state, and having either a CZ gate or sort of in physicsy language an Ising interaction on each edge of some graph. So Aij, we call the adjacency matrix. It specifies the graph of entanglement we'd like to create. And essentially, if we follow this prescription, what we'll get is a state where sigma x of the qubit on a given vertex is correlated with the sigma z's of the neighboring qubits. So that's perhaps the sort of picture that, if your background is in quantum information, you have in mind for sort of what a graph state is and how I might make it. And it's interesting in this context because actually if you can sort of make these graph states, you can subsequently actually do any computation simply by measurement, and the whole sort of hard process of generating entanglement is up at the front of your computation. So that kind of illustrates something about the power of these states. In our system, we don't have individual qubits on each node. We currently have these atomic ensembles, which I showed you earlier. I described in this picture of I can think of some vector and some quantum fluctuations around it. And it turns out that the right sort of language for thinking about the states we make is in a continuous variable picture. So I'm going to think of each ensemble as being well approximated, actually, by just thinking about it initially as being like the vacuum state of some oscillator. So there's some Gaussian fluctuations in 2 quadratures, which I'm just going to call x and p. And the graph state is the one that you would make by essentially having an interaction that looks like xi, xj for each edge on the graph between the vertices that edge connects. And what that does is it again generates sort of correlations between non-commuting observables, in this case p, at the vertex, and the x's of the neighboring vertices that are connected by the graph. Okay, so that is sort of a nice kind of example of asking, how much control can we get over the structure of entanglement in our system is to say, if you give me a graph, can I make that state? And In general, it's not really obvious that there's a sort of a good way to do this using the global interactions that we have, right? I said I want kind of arbitrary pairwise interactions. But it turns out that there is actually a really nice way to go from a graph that you give me to a prescription for making the state. And that involves basically saying there's some matrix, again, that specifies the graph. And the first thing we can do if you ask me, can you make this graph, is I can actually just diagonalize that matrix. Let me start with a minimal example. If I have just 2 nodes and an edge between them, that is a matrix you all can diagonalize in your head. This is actually an EPR type entangled state. If you diagonalize this matrix, you'll see that the eigenmodes are sort of symmetric and anti-symmetric combinations of the 2 sites. And the eigenvalues are plus and minus 1. It turns out the eigenvalues, so the eigenvectors I can interpret as essentially telling me collective modes that I should squeeze with my cavity. And the eigenvalues specify actually the orientations of the squeezed quadratures. Here the eigenvalues being plus and minus 1 says the squeezed quadratures should be at sort of opposite orientations. So that's the state I would like to make, and actually now the way that we can make this state in our setup is basically we want to essentially squeeze these 2 different collective modes. What we can naturally do is a global squeezing operation, but we also have local control, which allows us to do some pi rotation of the spins on one subsystem, so in this case the right pair of ensembles, and that actually maps the squeezing from the symmetric to the anti-symmetric mode. We can also do any phase space rotation to pick out which quadrature is squeezed. And then we can do one more global squeezing operation, and now we have squeezed both the symmetric and the anti-symmetric modes in orthogonal quadratures, and that was indeed our prescription for making this EPR entangled state. And that works. You know, one can characterize the state and see that the variance is minimized at 90-degree angles for these 2 different collective modes, and one can also map that back and say that means the structure of correlations is precisely the one that we set out to build. And in terms of sort of scaling up this programmable entanglement, you know, as just another example, if we go up to really caring about all 4 nodes, we can make, for example, the square graph, which would be this checkerboard correlation matrix. If you diagonalize that matrix, you'll again get sort of a set of 4 collective modes that one should have the cavity talk to, and it's a slightly more involved sequence of 4 global squeezing operations interspersed with local rotations, but that will build up then precisely this desired structure of entanglement in our system. Okay, so this is really kind of a general prescription. You give me a graph, I can build that structure of entanglement using just this sort of global interaction plus local rotation, those 2 ingredients. One question you might ask is kind of, you know, can you scale up in terms of both the number of modes, which I'll come to in a moment, and also sort of, you know, the strength of squeezing. We're just starting to dip by, you know, up to a factor of 2 below this line that's our standard quantum limit that shows there's entanglement. And actually in some recent work, we've been sort of one limitation actually in our system is just how well can one detect the entangled state. And it turns out there's fancier protocols one can use where one can actually, after preparing the desired entangled state, amplify the signal by essentially reversing the squeezing operation. So unsqueeze the axis that was previously squeezed before detecting. And with that, we can get up to kind of 7 dB beyond that standard quantum limit. And we can actually do that for any collective mode. So this sort of allows one in principle to also go through sequentially and for a more complex state, really get the full benefit of the entanglement out. So here's an illustration showing that we can do this for the symmetric mode of 8 clouds of atoms, but also for this kind of, I call it k equals pi, the mode where there's a pi rotation from site to site. This one is a thing that's sensitive to some global field. This is something that's sensitive to perturbations in some spatially oscillating field if you want to use this in a sensing context. Okay, so in general, if you want to, so that was sort of starting to look at 8 clouds of atoms. You might ask sort of how does this scale? The thing that I think is actually was initially surprising to us is naively you might think if you give me an arbitrary graph, I'm going to need like for m nodes, m squared operations to specify all the edges of the graph. But this sort of diagonalization, this procedure of finding collective modes says there's actually m operations that you can use to make any graph. There's sort of these m eigenmodes that we should couple the cavity to. And actually each of those operations happens at a collectively enhanced speed. So it's actually an efficient way to sort of prepare arbitrary structures of entanglement. Some are sort of more convenient to access than others, depending what you get when you diagonalize and look at your eigenmodes. But so, for example, one class of graphs that's very natural to access are translation invariant graphs. So if the graph is translation invariant, when I diagonalize, the eigenmodes will actually be spin waves. So essentially, just some phase factor that evolves from site to site in my array. And one way that you can sequentially couple to these different spin waves, I don't even need sort of arbitrary optical control. I can just allow my spins to precess in a magnetic field gradient. And what was this k equals 0 mode will actually at a later time evolve into a different spin wave mode. And that actually turns out to be a very natural way, in our case, to what we've applied this to is really kind of in larger systems starting to program in the graph of interactions as a tool for quantum simulation. So, so the picture that one can have in mind is I have this array of clouds of ensembles. There's a magnetic field gradient. That means that the sort of energy splitting between the spin states is growing as a function of position in this array. And as a result of that, in sort of a momentum space picture at each time, the cavity is essentially coupling to a different spin wave mode if I reference to kind of t equals 0. And so by controlling the intensity of the cavity field as a function of time, I'm basically programming in a particular dispersion relation for spin waves in my system. And I have really, if I have arbitrary control of this intensity versus time, which is easy, we can really kind of program in arbitrary dispersions for the spin waves. That's a momentum space picture. What may be actually even more intuitive is a real space picture, which is to say, if I modulate my drive field at some frequency, I'm going to, in this gradient, basically resonantly turn on a coupling between sites at a particular distance that's given by the modulation frequency. So in this example, if I modulate at 3 times the frequency difference between neighboring sites, I'll turn on interactions at a difference of 3 sites. So that is the principle that also works in the experiment. Here's an experiment with an array of 18 clouds where in the first case, we just turn on a magnetic field gradient and drive with a single frequency of light, so the intensity is constant. And in this real space picture, the way to think about that is, well, now that process, that sort of spin exchange process or the pair creation process of making +1, -1 pairs is only resonant for pairs of atoms sitting on a single site. But if one modulates the drive field so that there are 2 frequency components present, then you can resonantly turn on this pair creation process at a particular distance set by the modulation frequency. That's with just sort of a single sinusoidal modulation. I here turned on interactions at a distance of 10 sites, and that shows up in the correlations that we measure. But you can generalize that now to have a fancier waveform with sort of multiple frequency components present that will turn on interactions at sort of multiple length scales in the system. And you can use that to sort of build up a range of sort of interesting graphs. So here's just a gallery of a few examples that we sort of engineered in our system. You can put in periodic boundary conditions and make a ring like this. You can be fancier and make something like a Mobius strip. And you can also, by the phase of the modulation, switching from 0 to pi changes the sign of the interaction. So this is an example of, it's kind of a Mobius strip geometry, and some of the couplings are ferromagnetic and some of them are anti-ferromagnetic. Those are all things that are very natural to program in, just with sort of the frequency spectrum and the waveform of our drive field. Okay. These images are some sort of, we measure some correlations, and then we're able to reconstruct a sort of natural geometric representation where sites are plotted near each other if they're strongly correlated, and the bonds indicate the strength and sign of the inferred coupling based on the correlation. Okay, so that I think gives sort of an illustration that this, even with this global connectivity, combined with some spatial control, in this case even just a magnetic field gradient, gives and time-dependent control of our drive. We have sort of rich control over the structure of interactions. So far, these are still sort of graphs that look local, maybe in a higher dimension than the 1D of our cavity system. They're still kind of Euclidean geometries. You can even go beyond that and say, let's try to build something more exotic that I really can't build just by embedding having local interactions in 3 dimensions or something. So just as a fun example, here's a graph we built where we have interactions at distances that are powers of 2, 1, 2, 4, 8 sites in a chain of 16. And you can kind of measure the correlations that come about from that, and there's some exponent that says, are the interactions largest at small or large powers of 2? If they're largest at large powers of 2, then one gets actually some weird non-monotonic structure of correlations, but it turns out there's a nice way to visualize sort of the effective geometry of the system, which is to say, actually, the right way to think about these correlations is it's as if the sites of our array were sitting on the leaves of a tree graph. You can think of this as kind of a non-Archimedean geometry. It's sort of an exotic form of geometry. These bonds are trying to indicate sort of something. It's kind of, they come about from some coarse graining procedure, looking at the correlations, looking where they're strongest, drawing bonds, connecting those and thinking of it as a larger site. There's this tree graph that kind of pops out as a representation of the structure of the correlations in the system. And this is actually intended to sort of give us a toy model in the lab of the notion known as holographic duality, which is the notion that sort of, in some cases, something that looks like curved space can emerge as a natural representation of the correlations in a quantum system. So the quantum system is here sort of living on the boundary of this tree graph, which actually you can think of as a discretized version of a hyperbolic space. And so kind of is a first example of maybe that one could explore some notions coming from the field of quantum gravity, questions about is gravity something that emerges from entanglement in some tabletop kind of quantum simulation experiments. Okay, so I kind of built up for you this toolbox of how we can engineer programmable structures of entanglement and programmable interactions by coupling our atoms to light. And I want to say a little bit about kind of a recent direction we've been taking this in the lab, which I motivated earlier, which is sort of asking, can this be useful for probing some topological physics? And again, the kind of motivation is the whole point of kind of realizing topological states, or one point is that it gives a robust way of encoding information non-locally, which is wonderful until you maybe need to manipulate or access that information, and then it would be great to controllably turn on some way of sort of talking to non-local degrees of freedom. Maybe the cavity can let you do that. And there's a range of approaches demonstrated in cold atom experiments for sort of building up topological states of matter. There's sort of, I would say, generally speaking, maybe two paradigms. One is sort of build an interesting band structure that might have, we heard in Eugene's talk yesterday about this notion of kinetic frustration that one can get by controlling the phases with which some particles can hop in a lattice. Building up some topological band structure and asking through the influence of interactions, do I get some topologically ordered state? Or there's a more sort of controlled way of make a graph state, do a sequence of measurements that can allow you to make things like the toric code ground state, which has been done in, for example, experiments like Dolev talked about. So these are kind of two paradigms that you can take as a starting point, and you could use local interactions and then maybe use the cavity to probe these systems, or what I'll actually mention is that also the cavity itself can be a toolbox for, we talked about graph states, but also for sort of engineering band structures that could be interesting for studying topological physics. And so why do I say that? So sort of how should I think about this? We have this way of sort of programming in the structure of spin exchange interactions in our system. And I can really think of that as these spin excitations are some, I can think of those as bosons that can kind of hop between sites of the array with some hopping that I can program in. So there's kind of a mapping roughly of this system of interacting large spins to particles that can hop between sites of this array. And in general, there might also be some interaction between the particles on a site. We have control in principle of the magnitude and the phase of these hopping matrix elements by the way that we sort of modulate the light field in our system. We also, I showed you, have a choice of is it open or periodic boundary conditions. Those can be valuable sort of tools in our simulation toolbox. And then this, essentially the spin-spin interaction at zero distance on-site that maps into some, I can think of it as an on-site interaction for the spin excitation. So this really kind of looks like some sort of a Hubbard model with programmable couplings that could even be long range and programmable on-site interaction. And then the sort of new feature compared to sort of other toolboxes for simulating Hubbard models is we could have any long-range coupling we want, but also we could use the non-local aspect of the cavity to access non-local observables in a non-destructive way. So we wanted to sort of start to explore this toolbox. We haven't fully benefited from all aspects of it, but I'm going to sort of show an example where we take advantage of having kind of tunable interactions, the cavity enabling readout of non-local observables, and also sort of the choice of boundary conditions in the system. So as a simple test case for sort of exploring some topological physics in the system, we really started with maybe the kind of the simplest model one could write down that has a topological phase transition, which is the so-called Su-Schrieffer-Heeger model. It's kind of a dimerized chain where one has a nearest neighbor hopping, these, in our case of spin excitations, hopping within each dimer that I call J prime, and a hopping between the dimers that I call J. And as one, if the intra-dimer hopping is the weaker one, there's a topological phase which manifests in sort of two edge states that are spectrally well separated from the bulk, which are essentially localized on the left and right ends of the chain, symmetric or superpositions of those left and right ends of the chain. And then another kind of feature of this model is there's a topological invariant, which is essentially, if one looks at the relative phase between the two sites of the dimer as a function of the momentum in the system, that can either wind or not wind once as a function of momentum, and that is another way of sort of seeing whether one is in this topological phase. So to engineer this model in our system, we can, and this was observed in very nice experiments in Emmanuel's group in using cold atoms in an optical lattice. And so we sort of drew inspiration from that and asked, could you build this in this sort of new platform with cavity-mediated hopping of the spin excitations? And one can do that. In our case, to realize this sort of dimerized system, we don't just use a magnetic field gradient as in the previous slides, but we actually locally imprint an effective magnetic field. We do that optically in a way that allows us to kind of separately control by the spectrum of our drive field. We have one frequency that controls the hopping J prime and a different frequency that controls the hopping J, and we can arbitrarily tune the strength of those. We can also kind of initialize different spin waves in our system and measure the relative phase on the dimer in order to kind of map out this topological invariant that I mentioned earlier, known as the Zach phase, which either might essentially wind or not wind, depending on the relative strengths of J and J prime. And that allows us essentially, by looking at that phase winding as a function of the strength of the inter versus intra-dimer coupling, to see this transition from the topological to the trivial phase in our system. So this is just saying we have the tools to build this paradigmatic model, this SSH model, and to see that we can access a topological phase transition. And now, one sort of feature that I mentioned of this topological chain is that it should have these edge states. And one way to observe those is essentially initialize some spin excitations at one end of the chain. And if we're in the topological phase, we should actually see those excitations kind of oscillate from the left to the right and back, while sort of leaving the bulk largely unperturbed. And we indeed observe that. One can see sort of in the topological phase anti-correlations in the polarization, the number of spin excitations on the two edges that sort of match what we would expect for being in this topological phase. And that goes away in the case where in the trivial phase where the dominant coupling is the intra-dimer coupling. So that's to say we can see these oscillations of edge states in a small sort of minimal example of this SSH chain. And to do it, one thing we had to be very careful about was to make sure that these spin excitations can hop between sites, but that there's no interaction between the spin excitations on a given site. So we had to actually play a trick in some sense in the experiment to tune the on-site interaction to 0. That trick involves actually having a set of blue detuned and a set of red detuned drive fields relative to the cavity resonance. So without going into too much detail on that, I'll just say by sort of tuning the imbalance of these red and blue detuned drive fields, there's a trick for basically tuning is there 0 on-site interaction, or controllably turning on this on-site interaction term, which allows us to then ask how are these edge state dynamics affected if the spin excitations on a given site do interact. So here's, so the blue curve here is the non-interacting system where there's some oscillation between the edges. And then as we sort of crank on this on-site interaction, you can see that that oscillation goes away. And so this is starting to show, some effect of turning on interactions in the system, which what I found useful is to have some sort of toy model for thinking about, what's going on here, why does the oscillation go away? And the toy model that we came up with is to say, well, in the limit where I can sort of think of these edge states as sort of isolated from the bulk, it's effectively I have some model of two bosonic modes with some coupling between them, which is essentially, I'll call it H, it's the gap in energy between the edge states, and some on-site interaction that we can tune. And this is essentially a well-studied model of a bosonic Josephson junction, which has a phenomenon that occurs called self-trapping, where if the on-site interaction becomes large compared to the hopping between these two modes, which in this case are the left and right edges, one expects that population indeed becomes sort of localized on one side. And there's really a nice kind of picture in phase space if I sort of think of the left and the right as these two modes, as the sort of top and bottom poles of some kind of a Bloch sphere. One can really visualize in phase space the dynamics, not just in the population basis, but also in kind of the relative phase of the two edge modes, where for large interactions, one expects to basically have some fixed points and some precession about those fixed points in these dynamics. So to sort of check whether this is the right picture for thinking about this edge state oscillation turning off, we asked the question, well, can we actually more fully map out these dynamics of the edge modes using the fact that we can actually measure the relative phase between the left and right edges by a sort of cavity interferometry. So we form a non-local interferometer between the left and right edges using the non-local cavity coupling. So we prepare some spin excitations on the left edge. We use the cavity to couple left to right. We evolve for some time under this SSH Hamiltonian, and then we do a second kind of cavity-mediated pi/2 pulse that, again, sort of closes this interferometer and measure the imbalance at the end, and that actually gives us a measurement then of the relative phase of the left and right edges. And that allows us to kind of map out the dynamics in this phase space where I think of the left and right sites as two poles of a Bloch sphere, and see that if I look at kind of the rate of change of the phase as a function of imbalance between the left and right, that sort of matches the model of what one would expect for this kind of bosonic Josephson junction. So I think this is a nice illustration of kind of a few features of the toolbox. We can kind of program in a desired topological band structure. We can observe the effect of tunable interactions. And we can even use the cavity as a non-local interferometer to really probe, in this case, the dynamics of the edge states in not only the population, but also the kind of phase quadrature. Okay, I think one fun direction to explore would be to actually go further in asking, can we really probe entanglement between the edges? And a prediction is that this on-site interaction should actually generate entanglement between the edges that wouldn't be present if the on-site interaction is off. And one could ask, can we see that by looking not just at mean field dynamics, but at quantum fluctuations in this system? Okay, so I've kind of shown you the beginning of a toolbox for probing topological physics with kind of this non-local cavity coupling, letting us also talk to non-local degrees of freedom, like these edge modes. There's more one could do by going beyond something that's a nearest neighbor chain that's realizable in other platforms to really use the flexibility to turn on long-range couplings, for example, to make flat bands and explore the influence of interactions and whether new strongly correlated states emerge there. I said I wanted to kind of comment at the end on, so far, everything we've shown, I can come up with a, simple model and calculate what will happen, because at the end it was mean field dynamics, earlier it was Gaussian states. So sort of one, I think, important question is kind of what are the directions for getting into a regime where one has some kind of quantum advantage in this system? And so one direction experimentally that we're interested in pushing is kind of, fewer atoms, stronger atom photon coupling, and there's a couple of different paths to doing that. I think what one would love to actually take some of these tools we've developed and combine them with not only kind of single atom detection, which is starting to be done in cavities, but also sort of strong enough atom-like coupling to actually have coherent dynamics in such an array of single atoms. So that's kind of one direction that's interesting to push. Although there's another sort of direction that we've been thinking about recently, which is actually even these sort of multi-mode Gaussian states can in some sense get you to an interesting regime for quantum advantage. And that's kind of inspired by thinking about their features for quantum sensing. So there's I think, sort of exciting recent theoretical proposal from the group of John Preskill that points out that if I have these EPR states that I showed you earlier we can make, and I have an array of such EPR states, one can actually get an exponential quantum speedup for a particular task, which is that of basically saying I have some field, let's say, that's displacing in phase space different modes of some sensor. I'm picturing here an array of atomic ensembles entangled in an EPR fashion with some reference states that are unperturbed. One can actually, if one wants to sort of reconstruct the probability distribution from which these perturbations here are drawn that are affecting these different modes, it's actually been proved that having access to EPR entanglement can give you an exponential speedup beyond what would be possible without having entanglement with this reference system. And the basic sort of element that lets you get there is that one has, for each mode, sensitivity to perturbations in two non-commuting observables. So in this case, I can have a displacement in some unknown direction in phase space. If I just had a single squeeze state, it might help me measure x, but not p. If I have an EPR entangled state, I can actually measure both x and p to better than any unentangled state could do. And the trick that sort of allows this is that as long as I have some unperturbed reference system that's called B, I can use the fact that I can simultaneously know both xa plus pb and I'll wrap up in a moment, and pa minus pb. These are commuting observables, and if I can measure both of them, there's no uncertainty bound. And that's the basic element of this sort of quantum advantage. So the sort of possible sort of subtlety or challenge is that these are non-local observables, the sum of the x's and the difference of the p's between these sort of spatially separated systems. But I just said that the cavity actually gives a way to access non-local observables. And so something we've recently been doing in the lab is actually preparing so far just one EPR state, using the cavity-mediated interactions to amplify these two non-local observables, the sum of the x's and the difference of the p's between two spatial modes. And that allows us to actually then measure in a basis where we can access the information from about two sort of non-commuting, about displacements in two non-commuting observables. And so one can essentially, for an arbitrary displacement in any direction in phase space, we can attain sensitivity beyond the standard quantum limit using this EPR entanglement. And so actually scaling this to more modes, which in principle is possible in our system, could be a neat way of demonstrating this actually exponential quantum advantage with the number of modes. So that's sort of, to kind of summarize, I showed you ways of programming entanglement and programming interactions. As one illustration, I showed that actually having this non-local connectivity of the cavity lets us access non-local degrees of freedom in this topological SSH model. And I've given you a path towards maybe taking these elements and moving towards a regime of quantum advantage. So with that, I will just thank all the people who make this happen, including actually Jonathan, who some of you may have met, who's in the audience, is a student who worked on these experiments. So ask him the hard questions.
So we have time for one or two questions.
Yeah, thanks for these nice new results on the SSH chain. So is there actually something also like fractional charges you can get to? Or, I mean, you're probing the band structure here and showing but I mean, can you when you go into this interacting regime, would there be something also like fractional charges that kind of?
So I don't know what the predictions are. Is that a prediction for the SSH model?
Yeah, I mean, if you fill the band with fermions, for example, if you would fill the band with non-interacting fermions, even just have a filled band and would put one particle on the edge, that would have a fractional charge.
Yeah, so I mean, I think that's an exciting direction. My instinct is that one probably has to go to this regime of, not 1,000 atoms per site, but probably single or few atoms per site. And again, I think that would be an exciting direction. And one, I think, neat point to make is that I showed this kind of cavity interferometry for probing the system, but that actually gets, I think, most interesting also when you have kind of one excitation per site or want to maybe get into this regime of seeing some strongly correlated states. So probably, maybe not yet. But I would say actually there's some phenomena that one might hope to see signatures of, so maybe not yet fractional excitations, but some kind of pairing phenomena in some of these flat band models, where I think by looking at the quantum fluctuations, one could see evidence of particles that can sort of not move individually, but can move in pairs. And so, yeah, and so I don't know about fractional excitations, but I think this would be fun to think about. There may be something where there's a signature in the quantum fluctuations. So yeah. Mm-hmm.
Thanks for the great talk. In the squeezing results, did you actually achieve the quantum Fisher information, like the variance that you would get as predicted by the quantum Fisher information?
So I think what you're asking is basically, by using the squeezing, are we getting like really the full metrological benefit of the state, or is there some larger quantum Fisher information that we're not fully Is that the question?
Yeah. So like you did this like time reversal thing to achieve the optimal measurement. I'm asking how close that measurement is to the actual
Yeah. So exactly. So we didn't directly check that, but what I would say is there are cases where you get to non-Gaussian states, and actually we had sort of proposed this time reversal measurement a number of years ago in a theory paper where the goal was to get to some sort of over-squeezed non-Gaussian state and still get close to sort of the maximum benefit that the Fisher information would predict. So I think that's one really useful application of this kind of cavity-based, interaction-based readout. In this case, we're sort of dealing with early time dynamics where the states are still well approximated as Gaussian. We didn't directly check that in the experiment, so there's maybe room to check, but I think that naively I would expect that it's more just about beating detection noise. Yeah.
All right. Thank you. So I think we'll have to move on, but let's thank Monika again.